Hello, everyone, and thank you for attending today's session. My name is Mark Donner. I'm a Senior Manager with the Environmental Innovation Team at Alberta Innovates. This is the third webinar in the 2023 Water Innovation webinar series. I would like to take a moment today to respectfully acknowledge that we are coming to you virtually from Treaty 6 and Treaty 7 territory and Métis Regions 3 and 4 in Alberta. I will highlight that the reach of this work and its activities influence and are influenced by all treaty territory and all Métis regions in Alberta, not just those from which we're coming to you today. This acknowledgement respects the histories, languages, and cultures of First Nations, Métis, Inuit, and all Indigenous peoples of Canada, whose presence continue to enrich our vibrant community. For those of you not familiar, Alberta Innovates is a provincial corporation created to support research and innovation activities. We provide funding programs, advice, connections, technical expertise, and applied research services. Our scope encompasses the whole innovation journey from applied R&D through to commercialization and end use. This includes science informing policy and practices. Water innovation webinars share ideas and outcomes from projects funded through Alberta Innovates Water Innovation Program and highlight other important water initiatives within the province. I hope this session will provide you with some valuable information and spark discussion. If you have any questions during the webcast, you can submit them through the Q&A box. We will try to answer as many questions as we can after we hear from all the speakers. This session chat box is a useful tool to connect with other participants. I would encourage you to use the tool to discuss the session topic, but please don't let it distract you from the presentations. With that, I would like to welcome everyone to the Alberta Innovates Water Innovation webinar. Today's topic is titled Using Isotopes to Study Climate-Related Changes in Our Water Resources. The impacts of climate change can be clearly seen in our water resources. In Alberta, water quality is changing and water supply is more variable and increasingly uncertain due to extreme weather events. Stable isotopes have been used to investigate water balance processes and the relationships between hydrology, vegetation, and ecosystems. These tools can help build an accurate baseline of water resources to better understand potential future states. So this webinar brings together 4 researchers who are using isotopes in different ways to characterize how climate change is affecting our water. Today, you'll hear from Dr. Tricia Stadnik, Professor and Canada Research Chair at the University of Calgary, Francisco Castro Munoz, Senior Researcher, Environmental Services at Inotech Alberta, Dr. John Gibson, Principal Researcher, Environmental Services, also at Inotech Alberta, and Dr. Bernhard Mayer, Professor, University of Calgary. All right, with that, we can get started. So, Tricia, you are first up. If you'd like to unmute and start sharing your presentation.
Sure. Can you hear me okay? Hopefully.
Yes, you're good to go.
All right. Thank you. So good afternoon, everybody. I'm Professor Tricia Stadnik from the University of Calgary Hydrological Analysis Lab and a professor and Canada Research Chair in the Schulich School of Engineering. So global climate change, as many of us have already been aware of, is increasingly altering the hydroclimatic responses in the hydrologic landscape beyond the range that is generally considered to be predictably possible from our hydrometeorological records alone. That is, the observations just don't simply capture the kinds of extremes that we're seeing. Water resource practitioners are often therefore increasingly reliant on new methods of modeling hydrological change. And a few key problems and barriers to the uptake of some new modeling advances exist. One that I'd like to discuss is shown here, which is the data availability issue, and we'll talk about on the next slide as well. Non-stationarity, which is that the records simply don't capture the trends, and the trend analysis tools that we have are extending beyond the stationarity issue, which means they're no longer applicable to us. And large-scale heterogeneity. So when we look at the things as a whole watershed scale, things are changing so rapidly that some of the modeling methods and tools that we have aren't able to capture the actual changes that we see. And this has a compounding causation and multifactorial effect on our ability to accurately predict the extremes. Okay, so consider observations of extreme flows that we use for flood frequency analysis as an example. And these are the same kinds of observations that we use to calibrate our models. Here, we see significant differences between selecting what we consider to be the AMAX flow series, which is the annual maximum flows, and that's shown in blue, from the instantaneous peak flow, or the IMAX series, which is shown in orange and is captured from 5-minute gauge recordings. There's often greater than 10% difference between the IMAX and AMAX observations of extreme flows. And typically speaking, the IMAX is always greater than the AMAX. Normally, what we calibrate our models to is the annual time series of flows, or the AMAX series. Another issue that we have globally are record lengths. This gauge in particular has data from 1945 to present, which represents a typical to actually longer period of record in Canada. The mean is about 50 years actually. And when we apply the rule of 2T, or 2 times the return period for flood frequency analysis on our observations, this means that if we're estimating 1 in 25-year event, we need at least 50 years of record. And so for large water infrastructure, which we typically design to 100 or 200-year return period, we simply don't have enough observations to accurately simulate that and model it. Furthermore, if we examine the hydrometric network design, then we find that the majority of the gauges in the world for hydrometric data are in fact focused at regional scales, so between about 1,000 and 10,000 square kilometers. And this is actually taken from a report from the World Bank for the World Hydrometeorologic Observing System. And essentially, this is, of course, driven by the need for operational data. So these gauges are installed mostly for flood forecasting purposes and to gather information that could be used for predicting flows that would be important to move people and mobilize resources. From a modeling perspective, however, this results in operations preferentially selecting lumped type models that run more efficiently at these larger scales than distributed and detailed hydrologic models, where we simply don't have enough data oftentimes to calibrate the level of complexity that those models have. But what do we miss when we actually turn to lumped models? And this is a very complicated graphic, but I'll try to break it down for you here. Well, local scale heterogeneity and connectivity between hydrologic storages and fluxes does tend to get averaged out across larger scales or watersheds. It is precisely these process scale changes that remain critical as early warning tools for climate change, and that are critical for generating peak flows that we need for understanding the effects of climate change on the hydrologic cycle. Shown here is the Athabasca River watershed, about 160,000 square kilometers. And there's different process sensitivities represented by the different colors and the little pie charts that you see for each hydrometric gauge within the basin. There's significant differences in the sensitivity of the model to specific processes as you move from the headwaters at the upstream. You see here it's dominated by glacial melt. That makes sense because of the Athabasca ice fields. Moving towards the mid-basin, then it becomes dominated by soil storage processes and retention. And as we move further downstream, then you become more dominated by evaporation and sometimes snowmelt type processes. So the question is, what do we care about in the model, and what are we willing to sacrifice if we model this entire basin as one lumped system and kind of find an overall average, which is shown by the basin mean here? The basin mean can be highly different than the individual sensitivities of processes and importance of those processes at specific gauges. What's happening here is the model and the processes are responding to changes in climate, land use cover, soils, and other aspects that are changing. So the larger that the basin gets, the more diverse and heterogeneous it gets. And there's really no one size fits all picture. So the takeaway here is that we need complicated yet efficient models that will provide us accurate predictions of extremes and changing processes for operational decision making. And this is where large-scale tracer-aided modeling can actually help us, because it provides additional data and provides feedback to the models that can help us to constrain some of these process-based predictions. So how can some of the advances in tracer-aided modeling help us to predict extremes under a changing climate? So starting with a recap of what I mean by large-scale tracer-aided modeling, essentially, it adds a computational step or function that tracks not only the water balance, but the mass exchange for every single storage and flux within a hydrologic model. So every time water is moved as a flux, mass is moved as well. And the isotopes are a useful tool because they are conservative and only change under the influence of evaporation or mixing of different sources. This helps us to specifically track storages that are affected by changes as a result of things like evaporation. We can improve model calibration and validation by using tracer-aided simulation in a couple of ways. First of all, we're improving the amount of data that's available to the model. So instead of calibrating to stream flow alone, we can calibrate to stream flow and the stream flow isotopic signature, if we collect that from the river water. But we can also grab samples from the environment, such as wetland complexes or soil storages or precipitation, and we can use those to constrain the model at the process level rather than at the final summative step of where it generates and routes stream flow. So in particular, this is a code that my group develops, and it's available on GitHub, and we're currently making it a model agnostic version that can plug in with any different hydrologic model. And we've already implemented this code within HYPE, which is the Swedish Meteorologic and Hydrologic Institute model. Okay, so in terms of directing individual hydrologic model calibration, we can compare and contrast model evaluation and an output that is calibrated to streamflow only versus that is calibrated by both streamflow and isotopes, which is helpful to us. The bottom left shows a hydrograph of an output from a calibrated model that was in blue, optimized only to the streamflow, versus in purple and this reddish pink color optimized to both flow and isotopes. And really what we take away from this is there are insignificant differences in the quality and accuracy of the total flow simulation. So there was no change detected no matter how we calibrated the model in terms of streamflow. But if we move to the top right, despite there being insignificant differences in streamflow, internally within the model, there can actually be very large differences in terms of where that water's going and where it's being stored. The radar plots, each corner represents a different storage compartment within the model controlled by different parameters. The left one is from the flow only calibration here. So the one that I'm circling, or plot A. And essentially it's showing that it's dominated by one process with quite a bit of uncertainty, as shown by the gray bands, and then two other processes, which really are indicating a difference from when we add the isotopes to the calibration. It's almost completely opposite, where the water is stored in a completely different place in the model and different processes are controlling the flow response. And so this should be concerning to us as modelers because we don't see any difference in the total flow simulation, yet internally what's happening in the model is entirely different under these two scenarios. We've also taken a look at the cost of increasing model complexity by adding isotopes to calibration, and we can actually achieve near equal model streamflow performance, which is very important from an operations or practitioner point of view. And so this is showing the KGE of flow, which is a metric that we use. The maximum value is 1 versus the KGE of oxygen 18. Again, the best value is 1. This is for a basin, though, where we have fairly limited data and a large scale. So we wouldn't expect to get KGEs of 1 in this case, but you can see that the best fit would be the top right corner here, also represented by the green shaded areas. When we calibrate with both flow and isotopes, so shown as the purple dots, then we can achieve the maximum stream flow performance as well as the maximum isotope performance. However, if we calibrate only to stream flow, shown as these blue or cyan dots, we do achieve a slightly higher KGE of flow, but at the expense of a pretty terrible isotope simulation, which means we're really not putting the water in the right compartments, and we're not evaporating enough from the model or storing enough in the soil. What is also interesting here is we ran a scenario where we pretended that we didn't have any flow data, and we calibrated the model only using isotope data, and then checked at how well it performed in terms of flow. And so this would be a scenario where we've got isotope data in an ungauged basin. And you can see that, it's not the greatest, but it does perform well isotopically, and it gives us a KGE value that is decent and respectable for large scale modeling. And so these isotopes also offer potential for predictions in ungauged basins. And though there may not be significant differences in total stream flow prediction in the short term, so this top graph here is showing the peak flow estimation relative to the observed, which is the black dots with the error bars representing the uncertainty in the observed record. When we run those exact same calibrated models, optimized only to streamflow and then optimized with both isotopes and streamflow, and we run that into the future, out to specifically here, 2070, then we start to see a separation of those different calibrations. And specifically, the model that's optimized with both the flow and the isotopes is the only one that really captures a larger range of extreme flows. Now, that's important because if you check out this historical observed point here, this is a 2017 flood that occurred in this basin. It didn't occur until after we did this study, but you can see that the model was grossly underpredicting the maximum extreme. So we do believe that models in general, when they're calibrated to streamflow only, are tending to underpredict extreme flows. So water balance is really the canary in the coal mine, and it's going to respond to climate change earlier than streamflow. Evaluating models by streamflow alone might yield high accuracy, a high KGE score, but it can result in low model fidelity. Basically, the isotopes are better tuned to detecting process-based changes from non-stationarity, and they see things that the streamflow doesn't. So when we add that to our calibration process, we're more likely to calibrate those kinds of scenarios and process combinations that lead to extreme flows. So we need to ask ourselves, what are our models actually good for, and what is needed from the modeling community in terms of moving forward, and how can isotopes help? Isotopes specifically can help us to address the predictions to operations gap. Shown here is a quote from an excerpt of Kenneth Arrow when working on the month-ahead weather forecast during the Second World War. And it's basically saying that the commanding general is well aware that the forecasts are no good. However, we need them for planning purposes. So just like the commanding general here, we need models and predictions of extremes for actual operational purposes. So despite the fact that they're not perfect, we know we need to rely on them. So how can we improve them? Improving the representativeness of the models requires us to think broader and more holistically. We need to connect the various systems that examine the cumulative effects of climate change. So how the climate and the land use changes affect the hydrology, but then how the human intervention, such as the regulation, also affects the hydrology, and how that trickles down to looking at ecological thresholds within the river. This requires us to add even more processes and more complexity to our modeling chain, in which we know for sure that streamflow data alone will not be enough to calibrate the models. A systems thinking approach is therefore demanded to focus on the system as a whole and how the parts actually integrate together. So what knowledge is needed from a policy perspective is that we feed the climate simulations into both the hydrology and hydraulics models, which then allow us to look at floodplain mapping. But instead of stopping there, we can actually integrate ecological and socioeconomic impacts using integrated water resource management modeling. And from there, integrate science-informed policy decisions into the sensitivity analyses that we do from the hydrologic models. So for example, socioeconomic impacts of climate change involve a human decision. That is not well represented, if at all, within the hydrologic models. But if we make a different choice in terms of where we put a culvert or a dam, then that will affect the temperature of the flow and the downstream ecological thresholds and minimum and maximum flows, which could have socioeconomic impacts that would then change the policies and decisions that we might make. Of course, there's going to be uncertainty in any modeling chain. And as we add more complexity, there's going to be even more uncertainty. So how do we deal with that? We can use isotopes to help support the next generation of decision-making and policy, because the accuracy of the models and predictions, of course, is a huge risk to operations. Isotopes, as I've shown, can help to highlight the model structure errors and improve the model calibration, which improves the reliability of the model outputs. Plus, we then subject our models to more testing, which actually increases the perception of accuracy as well. Isotopes are also enhancing the amount of data and observations that we have globally, not just in Canada, and opening up new data analytics possibilities as well for things like machine learning. Because isotopes tease apart processes, we can often detect changes in the hydrological processes using the isotopes long before we actually see a total change in streamflow. This then acts as an early warning for managers and an identification of hotspots of change that can link to biodiversity stressors. Isotopes also offer more evidence and more justification for decision makers in terms of providing more data to and additional evidence to help support the decisions. Over the past year, my team has also worked with Innotech Alberta to develop an interactive dashboard to help make isotope data more accessible to practitioners. The ISO ABMI dashboard is shown here and is a development of a visual interface to help display isotope data. So the functionality includes spatial mapping of isotope data that were collected under the ABMI program. And you can click on an individual site and then see where that site falls relative to the rest of the data in an isotope framework space. You can also use interactive toggles for different hydrologic processes and water balances, such as E over I, Q over I, groundwater over inflow, and groundwater over surface water, in order to display sites within a particular range of any water balance indicator. And last, you can also scale by watershed characteristics. So here I'm showing water yield, but we also have drainage area, lake area, and mean depth as scalable maps that can be used, where you can see the isotope framework and the individual isotope sites as well. So to sum up, the increased frequency of extreme events must be accounted for in our models and modeling methods. This demands a more complex and process-based approach, which will require us to improve our observations that we use to tune our models. Advances in large-scale tracer-aided modeling can help with methods that provide information on process partitioning within the models to improve our prediction of extreme events. Expanded modeling chains that look at the downstream consequences of water balance change are very important to help inform policy and decision makers. But to get there, we need to focus on developing user-friendly tools and open source models and codes and workflows that make this all accessible to non-isotope experts. So the moral of the story is that uncertainty will always prohibit models from being exactly correct, but large-scale tracer-aided modeling offers the opportunity to detect this uncertainty and to move it from being a threat to an opportunity for informed decision-making. Thank you.
Okay, thank you very much, Dr. Stadnik. Excellent presentation. A reminder to folks online, we're compiling questions. We'll have about 20 minutes at the end for a Q&A discussion as well. So I'll turn things over now to Francisco and John, if you could begin sharing your slides and unmute, please.
Okay, can you hear me?
Yeah, coming through.
Okay, thanks very much. Francisco and I are going to share with you this case study that applies isotopes to demonstrate water balance changes in a network of lakes in northern Alberta. And we've been looking at this, we've been monitoring these lakes for 2 decades, and we do see very significant trends. And I'd just like to tell the story of these lakes. What we interpret is happening here is degradation of permafrost, so it's thawing, and additional water is being generated from this from the storage of that was once in permafrost, and it's flowing to these lakes. And across the region, the lakes are all in a different stage of progression in this permafrost thaw. We call it the thaw trajectory. And just here on the front page is a picture of frozen soil in a core that we collected near Namur Lake. I'm not able to advance. Hang on. There we are. So I'm going to start by talking a little bit about water availability trends in Alberta, and then show that a lot of these trends, or at least the ones in the north, are not explained by the precipitation and evapotranspiration trends. So they're not directly driven by changes in these processes, but rather by permafrost thaw. And the network of lakes, it's a group of 50 lakes, and RAMP stands for Regional Aquatic Monitoring Program. The network was originally set up to monitor acid rain and deposition, but we see some interesting patterns that don't support that acidification is happening. And part of the reason is because of the influence of permafrost thaw. So it's a case study that uses isotopes to trace changes in water balance and also to look at the changes in the geochemistry of these lakes. So I'm going to tell you a little bit about those isotopic trends, some of the evidence of permafrost thaw, and some of the implications of that. And Francisco's going to talk a little bit about the geochemical processes that are affected by this. This photo here is just from Google Earth, and it shows collapse fens adjacent to Namur Lake, which is in the Birch Mountains. And what is happening here is that it's a bog plateau, as per the cross section at the bottom, which is collapsing. And when you get early collapse, you get sort of pock marks or scars that are internal within the bog. But once they coalesce, they form collapse fens, and these can transport material, nutrients, carbon to the lakes, and they change the geochemistry, and they change the water balance. So in terms of water yield, this is a very recent publication specific to Alberta that was compiled and just released this year. And Newton and Taub here, they show the water yield trends for different watersheds across Alberta. Now, the most prominent trends that you see are that alpine watersheds in the south are shedding more water. They show positive trends, and this is over the period from 1976 to 2015. There are some declining trends in the north. And if we look here in the far north, in the lower Athabasca region, we see purple. That is the steepest increase in water yield anywhere in the province over that 40-year period. And I'm going to try and convey that to you that this is likely due to permafrost thaw. If we look at the climate data for the same time period, and I highlight it here in red and show it these arrows, it marks, this is for Fort McMurray, which is a nearby weather station in the lower Athabasca. It clearly shows a wet to dry transition during that 40-year period, and also looks like a decrease in precipitation over that interval. This does not explain increase in stream flow. The process that we attribute the changes to is permafrost thaw, and this is observed in the field at these 50 lakes. We show here in the left panel just a map of permafrost zones in Canada. We're looking at a region here which is right on the southern boundary of the permafrost zone. You know, sort of sporadic and isolated permafrost is present. Most of the time it's within bogs, and it's the peat that's very insulating that protects it and allows frozen conditions for more than 1 year. That's the definition of permafrost. So we have these lakes in different groups. There's 6 subgroups. They're colored differently in the middle plot here. And they range from the Stony Mountains in the south all the way to the Caribou Mountains in the north. And you can see one characteristic, this is sort of exaggerated topography, but it highlights the upland, these are plateaus that are lined by shale, and they're quite impermeable, and they tend to have permafrost in the north, but in the south, the Stony Mountains is more or less already thawed. So it's a permafrost thaw trajectory that has occurred over a long period of time since the Little Ice Age. That's a cold period that occurred between about 1300 and 1850. Now here I show aerial view of the collapse features and some of the collapse bogs. These are early stages. They form these little pock marks, and later on they form these collapsed fens. So just to give you an idea, we're looking at a network of 50 headwater lakes. They vary in size, but they're mostly less than 1 square kilometer, and they're wetland dominated. So more than 50% of the watersheds are either bogs or fens or open water. And some of the lakes are complex, others are fairly simple. But we've been monitoring these for 2 decades and looking at changes over time. So in each watershed, we went in and we did very careful mapping using air photos. We know the distribution of land cover, and we know the boundaries, the watershed boundaries. We measured the bathymetry of the lake. We know the volume, and then here's just a plot showing by subregion that we have variations in percentage of upland, fen, bog, and permafrost. Now these are the major features. You can see some regions have, some subregions have up to 80% permafrost by land cover percentage. If you organize them into different categories, we see 3 main types of lakes. We see fen-dominated lowland lakes, we see fen-dominated plateau lakes, and we see bog-dominated plateau lakes. And fens tend to have more groundwater influence, and bogs tend to have a lot less. And what we see is that the fen-dominated plateaus seem to be areas where permafrost is already thawed. And the lowland fen-dominated, they tend to be mostly permafrost-free. So for our analysis, we quantified the weather variables across our network using the North American reanalysis data set. And so we developed time series over the period. This is a 16-year data set that we interpreted. And we have a record of temperature, relative humidity, precipitation, and evaporation for each site. So this is information that's included in our isotope balance model, which I'll show you in a sec. The isotopic data is quite interesting. It sort of mirrors what Trish was showing for our ISO-ABMI network. We have the lakes are falling on an evaporation line, which is very characteristic of open water evaporation loss. It's distinct from precipitation patterns or input patterns, which I show here on a separate plot. So we have a contrast between input and lake water that we can use to tell us how much water is being lost by evaporation at each site. And we can track it over time and use that to solve the water budget. Here's the same 018 data. So that's just the one dimension, but it's showing the progression over time for each subgroup of lakes. So you can see here the variations. We we put this into the isotope mass balance framework, and we can calculate things like the evaporation to inflow ratio, so the fraction that's lost by evaporation. We can calculate the residence time of water, so how long is the water in the lake. The water yield is the it's shown here as the runoff. So it's the lateral input to the lake that's not accounted for. So you have precipitation and lateral input. We can calculate the lateral component, and we can develop an understanding of runoff components. So just to show you, here's just a summary of the quantitative information that we're able to discern from using this method. And I just show a summary here of some of the basic characteristics. I highlight here at the bottom in this graphic the contrast between two different plateau regions, one in the north, which is mostly permafrost bearing, and one in the south, which is mostly thawed. And we see the one in the south, we see water yield, so the runoff from the watersheds is mostly less than the precipitation. But the one in the north, the water yields are sometimes higher even than the precipitation. This is the related to permafrost thaw contributions to these systems. So they're getting way more water than they would if they had no permafrost thaw occurring. But this process is not constant. It's something that will wax and wane over time. We've determined that some bog-dominated plateau systems that are melting can yield over 300 millimeters per year extra runoff. That doubles the runoff if you look at those figures. So the process that we envisage here is sort of like a thaw cycle hydrograph, where we get early permafrost melt is in the category 1, and then stage 2 is when it starts to decline, and then we get stage 3 and stage 4. And we've classified all of our lakes according to this category. So we have a way of classifying whether the lakes are have above average water yields or whether they have below average water yields. That's on this lower axis. And then this is the trend. So is it a positive trend or is it a negative trend? And this tells us a lot about the position on the thaw hydrograph. So now the chemistry is also very interesting. Francisco is going to tell us a little bit about the chemistry of these lakes. Go ahead, Francisco.
Thank you, John. Okay, so this what I'm going to present in the 5 slides that follow is the summary of what we discussed in a Journal of Hydrology Regional Studies special issue that was published in 2022. If you want to see the more in-depth explanation of this hydrochemistry, you can go to that issue. So I'm going to talk about the hydrochemistry of the 50 lakes that initially were designed here as distributed in the left-hand side of your screen with the different lake groups, like John mentioned before, because they were thought they were acid sensitive, therefore they constitute what is called the RAMP lake, so the Regional Aquatic Monitoring Program that has been monitored over 2 decades, like John explained. In this study, we investigated the use basic statistics, principal component analysis, and lithological evidence and CO2 saturation estimates, as mineral equilibria and carbon-13 in the DIC measurements to describe and assess the controls on the pH, because what we see, as you can see in the right-hand side top, you see the trend of the pH that is increasing in a sigmoidal shape with the alkalinity. That trend seems to be flattening around the pH around 8, and when the alkalinity is reaching approximately 800 microequivalents per liter. This is very interesting because, as you can see in the right-hand side diagram, in the pH in the y-axis and the time on the x-axis, you see that there's a trajectory to increasing the pH with time. So that's what the question we're asking: why? What hydrochemical mechanisms could explain the continuous increase in these pHs with time? So, well, the first component that we see, you could envision that we were leaning towards understanding if the alkalinity was having an impact on the pH. It was the most obvious explanation. So we went to investigate the ion balances in these waters, and we found out around the majority of these waters have a deficit in the anions, so leaning more towards the cations, and then we identified that probably there was some negative ionic charge missing. But well, the explanation here is that the organic carboxylic acids in the ionic form probably are great contributors to the ion balances. When we compensated with the organic carboxylic ions, the majority of these waters went within the acceptable ion balance errors. So that confirmed that the organic matter associated to the dissolved organic matter associated to the water of these lakes is an important component in the ion balances. The next, please. So when we plotted the chemistry in a simple box diagram, we observed that these lakes in general have a calcium bicarbonate composition. And then in some lakes where we see the orange arrow in your screens at the bottom, you can see the carboxylic acid component as part of the imbalances. So in some groups of lakes, the carboxylic acid play a significant role, more than in others. And that's associated to what John was explaining, that about the permafrost melt connected to the dissolved organic matter. So the permafrost melt injects an additional dissolved organic component into the acid water that makes up the missing ions in the ion balances. Also, we've identified that these waters have an important component in terms of color. So some of them with less color and low pHs are associated to some lakes with more permafrost melting, and associated to what John mentioned, that the bogs that have more surface water component, whereas those with a high high colors are associated probably more to a groundwater component. So next. So the other technique that we use to explain the hydrochemical process occurring in these lakes are what is called the PCA multivariate statistical analysis that were applied to identify the relationship between the pH and other physical-chemical components between the individual lakes. So as you can see in this graph, most of the lakes in the vertical axis is a positive value, whereas in the lower part of the y-axis is negative. So the most positive values are leaning towards color, nutrients, turbidity, total suspended solids, and ammonia. And then in the right-hand side, where you see positive values in the PCA, in the principal component 1, the top lakes show a consistency when the pH is associated to the dissolving organic carbon, the alkalinity, calcium, magnesium, and TDS. So this intuitively will lead us that they confirm that the alkalinity is a major component controlling the pH, and also the dissolution of carbonates is a major process in these lakes, in these different groups. To highlight here is the ion, the chloride ion, that is conservative, and in the top group is the chloride seem to be aligned with the total suspended solids, turbidity, and ammonia, and color, and less associated to the dissolution, potentially dissolution of carbonatic rocks. Whereas in the lower groups, the chlorides seem to be, at least in the two groups on the left-hand side, in the bottom part of your graph, you will see that chloride is aligned with alkalinity, and then with the calcium magnesium, which means that more likely the rocks that dissolve in these systems have a component of salt component, and we have seen also in this region that some lakes and some natural springs have high saline waters, which is also reflected in some of these lakes, particularly in the northeast of Fort McMurray group, that is the great side on your left-hand side, the northeast, and the Stony Mountains. So the next. And then finally, when we look into the isotopes carbon-13 in the DIC in the right-hand side, you will see a trend increasing your values in the carbon-13 in the DIC with respect to the saturation index of calcite derived from applying equilibrium modeling to these waters. So there is a correspondence between the calcite dissolution and precipitation and the positive values of the carbon-13. On the left-hand side, you see the saturation index of calcite in similar fashion in correlation with the alkaline values. Basically, these graphs confirm that the dissolution of carbonates is a major component that is playing along with the dissolution of organic matter. In the circles, in the black circles in your right-hand side, you will be able to see which lakes are trending with high values of saturation index of calcite, and these values have high or in excess in CO2, dissolved CO2, which means that in these lakes you have high pHs, precipitation of calcite, and high values, positive values of carbon-13 in the DIC. However, we also observe that in some of these lakes, it's difficult to differentiate in the carbon-13 what is calcium carbonate and what is the result of methanogenesis. And we suspect that methanogenesis is also occurring in this system, but we need to do more investigation with regards to that process, because there are compounding effects here in the right-hand side in the graph. So finally, the last slide of this, where we will say that as a summary, the hydrochemical processes that are important for the ramp lakes that are reflective of climate change are related to carbonate dissolution, organic carbon dissolution, CO2 solution, and methanogenesis. There are some unknown temporal effects in these lakes that are primarily reflected in the atmospheric CO2 concentrations that are based locally, because we know that there is some CO2 emissions in this region, and also the chemical input from allochthonous sources, and most importantly perhaps is the reduced ice cover caused by spring and summer pHs increases associated to climate warming effects on the CO2 storage under ice. That is very important to highlight, because our samplings were always collected during the after melting, so we don't have samples collected over the winter under the ice. So if the CO2 get, like in the diagram in the schematics on the right-hand side, if the CO2 get increased and is stored during the snow and ice period, with these lakes get frozen and capped with ice, then as soon as the summer comes, this CO2 is exhaled to the atmosphere, and most likely the pHs are going to increase. So we need to research a little bit more, and in selected lakes, collect winter samples, and then that will help us to understand the CO2 effects over the winter to summer lake turnover. So that's all that I have, John. I think you have a few more slides to go.
Sure. I just wanted to briefly summarize. The headwater lakes tell us a lot about about the impact of permafrost thaw and on changes in ice cover and so forth, and changes in CO2 are part of that story, as Francisco mentioned. But the lakes display a range of water yield conditions. I showed you the way we classified. There's 4 categories generally. Either they're on the front end of just initially melting or thawing, or they are further along, depending on these categories here. So this is just a framework that we've used. I'd like to talk about the implications of the water availability or the water yield trends in the rivers after this, but I'll just summarize the headwater lakes first. pH is increasing in 46 of these 50 lakes over the last 2 decades. So this is exactly the opposite of what we thought when we thought these lakes might acidify due to acid emissions. But because of the influence of things like permafrost thaw and changes in lake cover, they are in fact increasing in pH. We suspect that surface groundwater interaction due to bog fen collapse is a major part of this. We can observe that happening. pH appears to be linked to the meltwater cycle, and it may actually decline once the permafrost thaws more significantly. And we're talking about a lot of water. This can double the water yield from a watershed for a number of years. We're not sure how long exactly, but we're continuing to monitor. The fen-dominated watersheds, we believe, are either post-thaw or in the advanced stages of thaw. So in terms of rivers, I showed you the purple area here, the highest upward positive trend in water yield. We believe that suggests that during the 40-year period from 1976 to 2015, we were still on the high side of melt, and maybe in stage 1 or on the rising limb, but that eventually we're going to go into a situation where the water yields are going down and down. This is going to happen in the alpine regions as well, where they're positive over the 40 years up to 2015. They're certainly going to wane over time, and less water availability is going to be the result. So that's going to change not only the flow regimes, but also the geochemistry, as we've shown. So we must anticipate this, and it's one of the direct sort of impacts of climate change on our water resources in Alberta. So as Francisco mentioned, we plan to do further field-based research to better understand the trajectory of climate change across the entire region of northern Alberta. Thank you.
Hey, thank you, John. Thank you, Francisco. We're rounding third, to borrow a term from baseball, and I'll turn it over to Bernhard Mayer.
Thank you, Mark. So my role is in the last 20 minutes of this presentation series to talk about groundwater. And I entitled this presentation Determining the Sources of Contaminants and the Age of Groundwater in Alberta Aquifers Using Isotope Techniques. And before I start, I want to acknowledge a number of co-authors from various institutions in Alberta and from universities in the United States and in Switzerland who have contributed to this work. Providing sufficient and sustainable amounts of high-quality water is of key importance for Alberta's economic future development. Where surface water is not accessible or where it is fully allocated, such in the southern part of the province, groundwater constitutes an alternate source of clean water. But one of the key questions we need to answer is to what extent can groundwater be used to supplement the availability of high-quality water under various climate change scenarios. Now, the knowledge about groundwater in Alberta and the age of groundwater and its quality, it's still somewhat in its infancy. Key questions which need to be answered are what natural processes control groundwater quality. Are there any noticeable anthropogenic impacts we can observe in the groundwater today? And most importantly, how old is the groundwater? Because the answer to that question will tell us how much groundwater can be sustainably pumped without negatively impacting groundwater quantity and groundwater quality, considering climate change scenarios. So the objectives of my short presentations are to summarize the current understanding of groundwater quality in Alberta on a province-wide scale, to briefly review the occurrence of select groundwater constituents such as sulfate and nitrate, and show how stable isotope analysis can reveal the sources or the fate of these contaminants. Then discuss approaches to estimate the age of groundwater using radioactive isotopes. And the goal of all of this research is to ensure sustainable use of groundwater under various climate change scenarios. So in order to achieve these goals, we use in principle 3 different methodological approaches. One of them is simply determining the water chemistry that includes pH values, dissolved oxygen, redox potential, the concentrations of major cations and anions, the concentrations of nutrients such as nitrate and phosphate, concentrations of minor and trace elements such as fluoride, manganese, arsenic, and others, and where available also the concentrations of dissolved and free gases such as methane and ethane in groundwater. This analysis is used to determine the salinity, the water types, and the redox state of groundwater in the subsurface. A second tool we are using is analyzing the stable isotope composition of various compounds, such as water, DIC, nitrate, sulfate, methane, and ethane, in select groundwater samples, which are typically obtained from the groundwater observation well network. On these compounds, for instance, nitrate, we always analyze the isotopic ratios of the 2 most abundant isotopes. And the diagram you see on the left-hand side shows you delta 15N values and delta 18O values of nitrate. And what you can see is that nitrate from different sources, such as precipitation, nitrate from inorganic fertilizers, nitrate from soil nitrogen, or nitrate from manure, has distinct and different isotopic compositions, and we can use these tools to determine the sources of dissolved constituents in groundwater. The third tool we use is radioactive isotopes to determine the average age of groundwater. In order to do that, we use environmental radioactive isotopes such as tritium, carbon-14, chlorine-36, and krypton-81 on very few select samples. For all these radioisotopes, if we know the initial concentration and we know their half-life times, we simply need to measure their concentration in groundwater and then can determine the age of the groundwater. So for tritium, the half-life time is 12.4 years, and we can date groundwaters as old as 70 years old. For carbon-14, the half-life time is 5,730 years, and we can date groundwaters as old as 40,000 years. And if groundwaters are older than that, we move to krypton-81, which has a half-life time of 229,000 years. And this trace allows us to date groundwaters as old as 1 million years old or more. In Alberta, groundwater samples for water quality assessment have been collected by various government organizations for many decades. What we have done over the last 10 years is we have amalgamated the groundwater quality information from 5 major sources and conducted a rigorous quality assessment and quality control analysis. That has resulted in 131,000 groundwater samples with groundwater quality information distributed across Alberta. On the right-hand side, you see the townships of Alberta distributed, and the color in the townships indicates how many groundwater samples we have with high quality groundwater information. What we can use this information for is determine the salinity of groundwater or the total dissolved solids. Total dissolved solids is simply the sum of all major cations and major anions, allows us to indicate the salinity of the groundwater. And by looking at all our samples, we found that about 2/3 of the groundwater in Alberta has less than 1,000 milligrams per liter. 1/3 of the groundwater in Alberta has total dissolved solids ranging from 1,000 to 4,000 milligrams per liter. And only 1% of the shallow groundwater in Alberta has more than 4,000 milligrams per liter of total dissolved solids. And that would be called saline groundwater in Alberta. The diagram you see is for each township, an average depths of the wells from which the water came, and the average total dissolved solids. The next slide shows on the left-hand side a frequency diagram of total dissolved solids or salinity for all groundwater samples in Alberta. And on the right-hand side, you see a map with color codes with the average total dissolved solids in each township for groundwater in that area. The only thing I want you to see is that the blue colors are all distributed on the left-hand side. So low TDS occurs mainly in the western foothills and in a region west of Highway 2, and that elevated total dissolved solids or salinities in groundwater do occur predominantly in the southeastern portion of the province. The total dissolved solids in the yellow, orange, and in the red boxes are higher than 2,000 milligrams per liter. The next question we can answer with our database is what contributes to the salinity? And we do that by determining major groundwater types. On the right-hand side, you see a Piper diagram which shows these types. And predominantly, we find 3 major groundwater types. In yellow, calcium magnesium bicarbonate water, which comes from carbonate dissolution and plots on the left-hand side of the Piper diagram. Then we find sodium bicarbonate water, which plots in the purple symbols at the bottom of the Piper diagram. And quite frequently, we also find sodium bicarbonate water, which has sulfate mixed in, which is a mixed water type on the Piper diagram. The next slide now uses groundwater age dating techniques on the right-hand diagram. On the x-axis plotted carbon-14 groundwater ages, and we show the different water types in different colors. And the y-axis shows the ratio of calcium over calcium over sodium in the groundwater samples. What I want you to see is that the yellow dots, which have the highest calcium concentrations and low calcium concentrations, invariably have the low ages. We also find tritium in these samples, as indicated by the crosses in the symbols. So freshly recharged groundwater is typically young and has a calcium bicarbonate water type. And as groundwater ages increase, we go towards the purple symbols where we have much higher groundwater ages, much higher sodium concentrations in the groundwater. So now we have a more geochemically evolved water with elevated concentration of sodium and much older ages. If we summarize all this information for the dominant water types and relate it to the salinity of the groundwater, we find that the young calcium magnesium bicarbonate groundwater has the lowest salinity with on average 400 milligrams per liter. The more evolved sodium bicarbonate groundwaters have increased salinity with 800 milligrams per liter. If we move towards the sodium bicarbonate sulfate water type, we have a yet higher salinity in the groundwater of an average 1,300 milligrams per liter. And if we move to sodium sulfate groundwaters, we see even higher salinity in the groundwater, now exceeding 2,000 milligrams per liter on average. This importance of sulfate to contribute to the salinity prompted us to have a more detailed look at the distribution of sulfate in groundwater in the province of Alberta. On the left-hand side, you see a frequency diagram showing you the concentrations of sulfate for all of our samples. And on the right-hand side, again, we show average sulfate concentrations in a given township, one average value per township. Sulfate occurs everywhere and often contributes significantly to the total dissolved solids of the groundwater. The Water Quality Guideline recommends that drinking water should have less than 500 milligrams per liter of sulfate, but our analysis has shown that about 22% of all groundwater samples in Alberta exceed that level of 500 milligrams per liter. And especially on the right-hand side in the southeast corner of the province, you see a lot of yellow and orange and red squares, indicating that there are numerous townships which have sulfate concentrations in excess of 900 milligrams per liter. In order to understand where that sulfate comes from, we use isotopic fingerprinting. This diagram is from a textbook. It shows sulfur isotope values on the x-axis versus oxygen isotope values of sulfate on the y-axis. The diagram really elaborates that sulfate from evaporites would plot in the top right corner of the diagram, whereas sulfate from a different source, such as sulfide oxidation, would plot in a very different region of this diagram in the bottom left corner. In addition, we can identify processes such as bacterial sulfate reduction, because if that process happens, sulfur and oxygen isotope values increase as sulfate concentrations decrease. On the right-hand side of the slide, you now see the observations we have made through sulfate isotopic fingerprinting of groundwater samples in Alberta. And especially for the samples with the very high sulfate concentrations having the large open circles, you can clearly see that all of this sulfate comes from the oxidation of sulfide minerals in the subsurface. So elevated sulfate in Alberta groundwater is almost always derived from pyrite oxidation, and this might happen either in the tills or in the marine bedrock in the subsurface. In some areas, and you see that indicated by the black arrow, we also find indication bacterial sulfate reduction is happening. And that indicates that this technique can not only identify the sources of sulfate, but also identify processes which remove sulfate from the groundwater, such as bacterial sulfate reduction. Another contaminant of interest in groundwater is nitrate, because excessive nitrate is a common problem in drinking water and causes various health effects. Because of that, Health Canada requires that drinking water has a maximum allowable concentration of only 10 milligrams per liter nitrate in. Excessive nutrients, including nitrate, can also cause eutrophication in surface water systems. You see on the right-hand picture from Lake Winnipeg, and on the left-hand side, an irrigation canal where macrophytes grow from the bottom and impact the delivery of irrigation water to the crops. In the worst case, this can lead to hypoxia or low oxygen in some waters, and fish kills might be a consequence. Because of that, we reviewed our database for concentrations of nitrate in groundwater. We looked at 90,000 records, and we found that in 2/3 of the cases, nitrate was below the detection limit. Only in 3% of all the samples we looked at, we found that the maximum allowable concentration higher than 10 milligrams nitrate N. And on the right-hand side, you see where these elevated nitrate concentrations predominantly occur. It's again in the southeast corner of the province of Alberta, where we have squares with yellow, orange, and red colors indicating that the average nitrate concentration in groundwater exceeds 10 milligrams per liter nitrate N. In order to understand what the sources of this nitrate are, of elevated nitrate concentrations, again, we can use stable isotope fingerprinting techniques. The diagram on the right-hand side shows you delta 15N and oxygen isotope values of the nitrate molecule. And for the majority of the samples, the yellow dots plot in the field, which indicates that manure is the source of nitrate if nitrate concentrations are elevated. In some cases, we also see that soil-derived nitrate is a source, and the soil in agricultural watersheds is often supplemented by urea and ammonium-based fertilizers. In addition, we see that some data points fall to the right-hand side of the boxes which are plotted, and that is clear indication that denitrification is occurring in this watershed. So again, we can use these stable isotope techniques not only to identify the predominant source of nitrate, which is manure-derived nitrate in this case, but also identify processes which remove nitrate from the groundwater, such as denitrification. In the last couple of minutes I want to come back to groundwater age dating and show you an example from the Milk River Aquifer, which is a cross-boundary aquifer where groundwater recharge typically happens in northern Montana in the Sweetgrass Hills, and then the groundwater infiltrates into the subsurface and migrates northwards into southern Alberta. The Milk River Aquifer has been studied for many decades, and the flow directions in this aquifer are relatively well understood. However, determining the sustainable yields of groundwater has been hampered by a lack of accurate age dates for old groundwater specifically. Because of that, we have conducted a project in the last 2 years where we tried to use refined and additional groundwater age dating approaches. We collected groundwater from the Milk River Aquifer on 20 different sites. They're all shown either in yellow dots or as red stars, and conducted groundwater age dating analysis. In this case, we show the results for carbon-14 age dating. And you can see that we only very near the recharge zone obtained carbon-14 age dating groundwater data, which vary from 17,000 years for the groundwater to 36,000 years. We also analyzed carbon-14 for all the other red stars locations, but in all of these cases, carbon-14 was below the detection limit, and that indicates that the groundwater must be older than 40,000 years. In that case, we need to move to a different tracer, another tracer, Krypton 81, which provides new constraints on the age of very old groundwater. In the vicinity of the recharge areas, we got results with Krypton 81, which are very much comparable to what we have seen with carbon-14, ranges between 20,000 years and 37,000 years for the groundwater. But as the groundwater moves further north, we now find even older groundwaters, in 2 cases varying from 200,000 years to 270,000 years. So in the middle of the aquifer, we already have groundwater, which is 250,000 years old. And we have further samples further north, which are currently under analysis. And here we expect even higher groundwater ages down gradient as the water percolates towards the north. This clearly indicates that we have very old groundwater and that infiltration of this groundwater must have occurred at very different climatic conditions way back in the Pleistocene. So to summarize now the key points of what I presented, knowledge about the quality of groundwater in Alberta's aquifers is rapidly emerging. Stable isotope techniques are effective in determining the sources, and to some extent the fate of groundwater constituents such as sulfate and nitrate, but this can also be expanded to methane and ethane. Recent advances in isotopic age dating techniques have greatly improved the knowledge of water ages, especially for very old groundwater. And it is the combined knowledge about the quality and the age of the groundwater which will be essential for determining how much groundwater can be sustainably extracted in the next few years, in the next few decades, and beyond under future climate change scenarios. With that, I want to thank the sponsors of this research, which are all shown here, and you for your attention. And I turn it back to Mark. Thank you very much.
Okay, thank you, Bernhard, and looking forward to seeing how old the water goes. All right, so we have some time left for Q&A. What I'll do is I'll read the questions aloud. And we're still going to look to wrap up at 2:30. So we might have to be concise in our answers somewhat, but I think we're okay on time. So the first one is for Dr. Stadnik from Tammy Rosner. It seems that current hydrological models do not even capture daily extremes, and acceptable performance standards do not consider extreme values, only overall least squares type performance measures. Have you given some thought to what performance measures and validation processes can be used to better focus on extreme events?
Yeah, thanks. Great question, Tammy. And yes, we've given a lot of thought to this. In fact, there's a publication that came out earlier this year or late last year, I can't remember exactly right now, by my postdoc, Tegan Holmes. We looked at 27 different metrics to figure which ones were the most representative for calibrating our models, and actually did try to zero in on the different types of flow, so low flow versus high flow. We also have other publications that have focused on low flows separately and high flows separately. There is no best metric, but KGE is certainly best for kind of the overall hydrograph, and Nash-Sutcliffe or NSE is the best for peak flow or extreme value analysis, and that's typically what we use when we're calibrating to peak flows specifically. Oftentimes it's a limitation in the observations or the data that we have that precludes us from calibrating any better to the peak flows. And that's just to say that we don't have a lot of observations of the extreme events. I mean, they're the most rare in the record. I think that makes common sense to a lot of people. So if you only have 1 or 2 data points to fit to, then that's all that you have to calibrate your model to at best, or validate it. And therefore the model just isn't able to capture or replicate those events with the same kind of accuracy.
Okay, super. Thank you. The next question is for John and Francisco. A number of the lakes you have been monitoring for the last 2 decades exist within proximity of a large industrial footprint of oil sands extraction, which also disrupts the hydrogeologic cycles. Has it been a challenge to distinguish broader environmental change, in this case permafrost melting, with local industrial activity?
John, go ahead.
Okay, yeah. One characteristic of the lakes is that they're headwater lakes, and they're not road accessible. So that most of the lakes are not really very close to direct impacts, right? So there's no direct impacts in the watersheds. The only exception was Curl Lake, and that lake is no longer monitored. It's now a tailings pond, and it's being operated as an industrial water reservoir. So we don't see a lot of direct impacts, but of course we only have limited information. None of these watersheds are gauged, so we are relying on the isotopic approach to estimate. So it's sort of Trish's situation in ungauged watersheds. We're using the isotopic signals in the lake to detect change. And I would say the vast majority is not related to industrial development directly, if that makes sense. Francisco, do you want to contribute to that?
Yeah, I would say that it will be challenging to separate the CO2 contribution from various sources. I think at the moment we only have modeled values of CO2. We don't have measured values of CO2 in the system. So that's something to address in the future.
Okay, you guys can stay unmuted because there's another one here for you. So from Jay White, what is the link between reduced ice cover and pH?
And John, can I take that one?
Yes, please do.
I would say that the relationship is that the climate change seems to be removing the ice cover earlier and earlier during the year. Therefore, the pH that will be affected based on the CO2 stored under the ice, so will be released earlier and earlier, affecting the readings on the pH in those lakes. I hope that kind of answered the question.
Okay, super. Thank you. Moving along, so a question now for Bernard. It seems like the groundwater in southern Alberta is lower quality, more saline. It is also the region where we will likely need to look to groundwater for future water supplies. Can you comment on the potential implications for future reliance on groundwater in southern Alberta?
Yeah, certainly the observation is correct that this southeast corner of the province of Alberta has challenging groundwater quality, but this is not the same everywhere. So now having an overview of where quality is, I think what needs to be done in the next little while is to find locations where the sulfate concentrations, nitrate concentrations are not extremely high, and find groundwater sources where we have reasonable water quality. It will not be perfect, and it won't be the same as in the foothills region where we have calcium bicarbonate type waters, but I think there's still potential to look in southeastern Alberta to find the relatively better groundwater and separate it from the more saline groundwater, which is neither good for drinking water purposes nor for animal purposes.
Perfect. Yeah. And so kind of a related, maybe add-on question. Have you looked at potential links between land use and groundwater quality in southern Alberta? So you mentioned manure and nitrates and other things. So maybe you could elaborate a little bit more on that.
Yeah, so we have currently a project funded which will look at the relationship between land use over the last 5 decades and the evolution of groundwater over time and its quality. So in 2 or 3 years, I might be able to present the results here. At this point, we only have sporadic observations where we have several groundwater samples with elevated nitrate and can relate it to manure applications in the vicinity, but that doesn't paint a regional picture. So the regional picture of land use change and how over time it has affected groundwater quality, if at all, will only emerge in the next couple of years.
Very good. A question now, I think for Francisco. So can radiocarbon or other isotopes be used to verify the release of DOM/organic acid as the missing component in the charge balance, or is that not necessary?
Yeah, then thanks for the question. Was like Bernard showed us earlier, the different ages for application of radioactive isotopes, radiocarbon, most likely won't be, I would say that would be less likely to be used to determine the or dissolved organic carbon or organic acids in these lakes, because it's a different measure, a different age range. Other isotopes that we have been exploring, and probably John hasn't mentioned it, we have been using radon as a radioactive isotope in the lakes, and then there could be other use of short measure isotopes. Another interesting isotope that seems to be giving a very good indication on this is tritium and the permafrost. So these are those two seem to be right. Is tritium, strontium, I would say, and radio and radon. Now, to be able to talk about the missing component in the charge balance, I think the best approach is the one that we presented, the approaches with the carboxylic acids. I don't see any other approaches to improving the ion balances. I hope that answered the question.
Can I just say a word or two? To follow on from what Francisco said, I think there are a lot of groups that are using carbon-14 in DOC to tag permafrost thaw contributions of older carbon. So, I mean, I think it is useful. It's not the carboxylic acid that Francisco's talking about, but it is potentially useful in tracing permafrost thaw contributions. So just wanted to add that.
Thanks, John.
Excellent. Thank you very much. Okay, we're getting near the end. If there are any final questions, make sure you get them in. So next question is Bernhard. What are the challenges and benefits of reliably being able to measure groundwaters up to 1 million years old?
Well, the challenges are mainly analytical. With Krypton 81, there's not very much krypton in groundwater. And about 20 years ago, you would have to sample thousands of liters of groundwater, extract the krypton. What happened in the last 15 years is that a new technology came online, which is called ATTA, Atom Trap Analytical Analysis of Krypton 81, which now relies on much smaller groundwater samples, and Krypton 81 has very little interference in the subsurface and subsurface production. So it is viewed as a highly accurate tracer for really old groundwater. What is the benefit? We want to understand, is the groundwater 250,000 years old, 500,000 years, or 1 million year old? Because we do pump groundwater out of the Milk River aquifer for irrigation and other purposes. And in the concept of sustainable yield, we only want to pump as much as can be replenished over time. So if the groundwater is 2 times or 3 times as old, the water withdrawal probably needs to be lower, as opposed if we pump younger groundwater. So that is how these ages will be used to kind of determine sustainable yields of groundwater, so that we don't overuse this precious resource.
Very good, thank you. Okay, so one final question before we close things out here. Is there a publication available yet on the age dating for groundwater contribution? Is this province-wide dating? So maybe a question for all, I guess. Or Bernhard and John and Francisco mainly.
So if this question is about age dating of groundwater, there is about 30 years of publications on various age dates of the Milk River aquifer. The current work we are doing with Krypton 81 will expand on that. The project will finish in March 2024, and then publications will probably come out after that. So the answer is no. The data showed it just preliminary data, which will be published next year. And other age dates, I showed some C14 data. They have been published this year by Ruff et al. 2023, which is mentioned in the presentation. And beyond that, I think there are various groundwater age dates, but there is no systematic approach which would have done this for all groundwaters in Alberta. And anybody else who wants to add on, please feel free to do so.
Yeah, I'll just say that we have published some carbon-14 age dating results from the oil sands region. That was contained in a COSIA publication, but it's also, I think it's in applied geochemistry as well. So there are, I think, 100 age dates in that publication. I can find that link and post it.
Sure. Okay. And all of the contact information is available as well if folks want to reach out and be connected to any of the speakers or ask other questions. We'd be happy to follow up. So with that, I'm going to bring things to a close. We're right on schedule, which is excellent. I want to say a big thank you to our speakers. Really great presentations. Personally, I'm exposed to this stuff a lot, and I still came away with some great takeaway messages and new information to think about. So I hope the discussion sparked some new ideas and provided new information for the speakers as well. The session is being recorded, and it will be available for future viewing. An email will be sent out when it's uploaded. And watch your emails for future sessions planned for 2024. So this is our last one for the calendar year. Our next webinar is currently planned for January 2024. The date will be sent out later once it's finalized, but I can say that the focus will be on hydrogen and water. So an exciting topic with lots of buzz around it. So with that, thanks, and we look forward to connecting with you all again soon. Take care.
Thank you.